Both of these PCBs from the GREE outdoor unit have failed in the same way. You can see how they got damaged. The capacitors have completely burst, with their aluminum sheets exposed. When we check the capacitor next to it, we see that it is empty and dried out, whereas the burst capacitor has its internal paper spread across the PCB copper traces. Similarly, when we inspect the second PCB, we find almost the same fault, but one capacitor appears to be somewhat safe as it has not exploded. But whereas this second capacitor has exploded, and the aluminum and protective sheet are also torn here. To check for further faults in these PCBs, we will remove them from their covers for a more detailed inspection. Now that we know the capacitors are physically damaged, the first step is to remove them. If we try testing the circuit with faulty components still in place, everything will appear to be defective. So, we will remove them one by one. To do this, we apply paste to soften the solder joints of the capacitors. Since the capacitor is no longer in place, we will push it out using a tool. As you can see, we have successfully removed it. Now we will remove the next capacitor, and it has also come out. Similarly, we will remove the capacitors from the second PCB. I had already applied paste to its joints, so we will push it from below, and it has come out. As you can see, it is moving internally. Now we will take out the other one, and it is also removed. Cleaning the PCB is very important because small aluminum pieces from the burst capacitors remain on the board. If these metal fragments stay on the PCB, they can cause short circuits later. That's why thorough cleaning is necessary to prevent any future issues. As you can see, after some time and effort, the PCB is now mostly clean. Now, let's start testing these PCBs. The first thing to check is the fuse. We set the multimeter to continuity mode and check the main fuse. As you can see, the main fuse is not working. Similarly, there is another fuse labeled FU102. We check its 2 points, which are the fuse terminals, and this fuse is also damaged. It is not working either. After checking the fuses, the next step is to test the switching IC. There is no authentic method to test a switching IC directly, but the method I am using will help us determine whether the IC is faulty or not. However, whether it is functioning correctly will only be confirmed once we apply power to the circuit. For this test, we set the multimeter to diode mode and place the probes on different points of the IC. Initially, no voltage drop is observed at any of the points. Then we reverse the probes, and now we see a voltage drop reading, 0.464 voltage drop on one point. Checking the last point, we get another voltage drop reading, 1.794V. This indicates that the IC is not short-circuited, meaning it is likely intact. However, whether it is actually working will only be confirmed when we supply power to the circuit. For now, we don't need to replace it, but if it doesn't function properly after powering up the PCB, we will replace it. Now, the next step is to check the high-side components, which include the IPM, diode, IGBT, and bridge rectifier. I have explained the method for testing these components in many of my videos. First, I tested the bridge rectifier by placing the positive probe on one side and the negative on the other, but no permanent voltage drop appeared. Then, I reversed the probes to see if it showed any values, and it displayed 0.473V. The next point also showed the same value, but on the last point, the reading was 00, which indicates that the bridge rectifier is short-circuited at this position. Next, I checked the IGBT by placing the probes on different points, and it gave a voltage drop of 0.578V. On another point, it showed 0.456V, which suggests that the IGBT is likely fine since we did not get a 00 reading. Similarly, I tested the diode, and on one side, it did not show any value, which is expected. However, after reversing the probes, it displayed 00, indicating that the diode might be short-circuited. Now, let's test the IPM. I placed the negative probe on the negative terminal and the positive probe on the positive terminal, then started checking different points. However, I did not get any voltage drop readings, which indicates that the IPM might be intact. Next, I reversed the probes, placing the positive on negative and negative on positive, and this time, I got a reading of 0.459V. On the next point, the reading was 0.481V, and the other points showed similar values. This suggests that the IPM is likely fine on the high side. However, we cannot confirm this 100% until we replace the diode and the bridge rectifier and ensure that they are functioning correctly. Now, we will test the second PCB using the same procedure. First, we check the fuse, and as you can see, this fuse is working fine without any issues. Next, we test the SMPS fuse, but it is not working. Now we move on to the bridge rectifier by setting the multimeter to diode mode. Initially, no values are displayed on any points. After reversing the probes, positive to negative and negative to positive, we see that values are appearing at multiple points. The readings are consistent across all points, which indicates that the bridge rectifier is working fine. Next, we test the IGBT, and it shows a voltage drop of 0.579V. After reversing the probes, it still shows correct values, meaning the IGBT is likely fine. Then we check the diode, and we observe a slight voltage drop that quickly disappears. After reversing the probes, the reading shows 0.030V, which confirms that this diode is short-circuited. Finally, we test the IPM, Intelligent Power Module. No values appear on any points initially, so we keep the positive probe on positive and the negative on negative while checking. The readings show 0.483V, 0.479V, 0.480V, and the last point also gives a similar value. This indicates that the IPM is likely in good condition and may be working fine. Now, let's check the switching IC to ensure it is not short-circuited. Placing the probes on different points, we observe a voltage drop of 0.671V, which indicates that the switching IC is not shorted. However, even if it is not showing a short circuit on the multimeter, there could still be minor internal faults that are not detected in this test. As we check different points, there is no significant voltage drop, except for one last point where a value is displayed. To fully confirm whether the switching IC is working correctly, we will need to power up the PCB and check its functionality under actual operating conditions. Finally, the last component to check is the microcontroller, but this test is not an authentic confirmation of whether it is functioning properly, especially for high-side operations. To perform this check, we set the multimeter to continuity mode. Around the microcontroller, there are several capacitors. The method involves checking continuity across all these capacitors because in some way, at least one capacitor will have one side connected to positive and the other to ground. This allows us to determine if the microcontroller is short-circuited to ground. If we hear a beep on any capacitor, it indicates that the microcontroller is grounded, meaning it has a short circuit. Ideally, there should be no beep on any capacitor. However, the final confirmation of whether the microcontroller is actually working will only be determined after powering up the PCB. As we check, there is no beep on any capacitor, which suggests that the microcontroller is likely fine. Now, to test the fan IPM, it is important to check all the surrounding capacitors thoroughly. Checking the first capacitor, it is completely fine. The second capacitor is also in good condition. Moving to another capacitor, it is working properly as well. Finally, we confirm that the multimeter is functioning correctly, ensuring that our readings are accurate. Since there is no beep on any capacitor, this means all capacitors are in good condition. Now, checking the second PCB, we find that the main fuse is okay, but the subfuse is not working. This means that repairing this PCB will be relatively easier. So, we will start working on this PCB first. In this PCB, the first step is to replace the faulty fuse. However, I initially made a mistake while testing. I was checking at the wrong point, where a capacitor was located instead of the actual fuse position. After realizing this, I checked the correct fuse location again, and it turned out that both the main fuse and the subfuse are perfectly fine. The reason I initially didn't get continuity was that I was testing the capacitor instead of the fuse. Next, I moved on to the diode, which was previously showing a short circuit. I have now removed the diode from the PCB. After retesting the same position on the PCB, there is no longer any short circuit indication, which suggests that the short circuit was caused by the diode itself. Now, testing the diode separately, it shows 0V, confirming that it is indeed short-circuited and needs to be replaced. Now we will install a Daewoo 450V 470 microfarad capacitor. This is a new capacitor, and for testing purposes, I will install only one capacitor at this stage. After placing the capacitor, we clean the diode mounting area to ensure a proper connection for the new diode. Both sides of the area are cleaned before installation. Next, I install the new diode, but I am not soldering it yet. Instead, I will align it with the heat sink so that it fits properly in its place. Even if we don't tighten the screws of the other components, the diode will still stay aligned. After installing the diode, I test it again. The multimeter shows a voltage drop of 0.362V, indicating a proper connection. After reversing the probes, no voltage drop is detected, which confirms that the diode is working correctly. Now, in the second PCB, the main fuse is blown, so we proceed to cut it from both sides. As you can see, it has been successfully removed. Next, we remove the faulty diode and test it separately. The multimeter shows 0V, confirming that the diode is completely short-circuited. Since a faulty diode can sometimes cause issues in the bridge rectifier, we recheck the bridge rectifier. The point that previously showed 0V still remains at 0V, indicating that there is a problem in the bridge rectifier as well. To confirm, we remove the bridge rectifier from the PCB and test it again. After testing separately, it is clear that the bridge rectifier itself is faulty, as it still shows 0 voltage drop. Other than this, there doesn't seem to be any additional fault on the PCB. However, to be completely sure, I thoroughly rechecked the PCB for any other potential issues. Skipping this step could lead to overlooking another hidden fault, which would be a mistake. After rechecking, there are no other faults on the PCB, meaning that only the bridge rectifier needs to be replaced. Now we will power up the second PCB to check its functionality. After connecting the electricity, the indicator lights turn on. Both the green and red LEDs are lit, confirming that the circuit is receiving power. Additionally, the switching process is working properly. Earlier, when I checked the switching IC with a multimeter, I had a strong indication that it was in good condition, as it did not show any faults. However, if by chance it did not function correctly, I would have replaced it and tested again. Since there are no issues with the switching IC and the entire PCB is functioning correctly, it confirms that the repair was successful. Now we will test this circuit board here. I have already set all the necessary settings. At the moment, the indoor unit is in an off condition, while the green light is on in the outdoor unit's circuit. So, I will start it now. It has started operating at 18 degrees. The indoor fan blower motor has also started running, the outdoor fan motor is running as well, and the compressor has successfully started. Now, I will check the suction and discharge. The suction is perfectly fine, and the discharge line is also okay. It is working properly, and all the IGBTs are switching correctly. Its speed has also started increasing, so now we will turn it off. Now, I have also installed the second circuit board. Let's turn it on using the remote. It is operating at 17 degrees. We will wait for a while. The indoor fan motor has also started. This circuit board, which I showed you earlier, is now ready. The LEDs on the outdoor circuit board are lit, and the outdoor fan motor has also started running. The compressor has also started. As you can see, everything is working perfectly. All the IGBTs are switching on. Now, I will check the suction and discharge. Both are absolutely fine and working efficiently. So, this circuit board is also completely okay. You have seen how I repaired it, and now I will turn it off using the remote. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.